Welcome to our deep dive into production readiness for LLM applications. In this video, we'll explore the critical aspects of deploying, monitoring, and maintaining large language model systems in enterprise environments. From logging and prompt versioning to CI/CD pipelines and robust deployment architectures, each topic is designed to help you build resilient, scalable, and secure AI solutions. Let's kick off by understanding why these foundational practices are essential for any organization aiming to leverage LLMs in real-world scenarios. Let's start with OpenInference, an open standard that extends OpenTelemetry for AI. OpenInference enables you to trace and capture LLM application behavior in a standardized way. It tracks metadata like prompt inputs, token counts, latency, and tool calls, feeding this data directly into monitoring systems such as Phoenix, Datadog, or New Relic. Imagine an MLOps engineer using OpenInference to trace a slow LLM response, pinpointing exactly which tool call or model invocation caused the delay. This transparency is crucial for debugging and optimizing production pipelines. Prompt versioning is vital in enterprise environments. By decoupling prompts from application code and treating them as configurations, you can store them in Git repositories or specialized registries like LangSmith or weights and biases prompts. Using semantic versioning and tagging production-ready prompts allows dynamic fetching via APIs. For example, when a team updates a customer support prompt, they publish a new version and tag it as production. The backend fetches the update instantly, without needing a full redeployment or server restart. Storing LLM conversation logs strictly in relational databases like PostgreSQL can be problematic. These databases struggle with the highly variable, nested nature of agentic steps, such as chains, recursive tool calls, and child spans. Distributed tracing systems or document stores are much better at visualizing execution trees and parent-child relationships. For instance, an agent performing multiple vector lookups and tool calls can be logged as a clean, nested JSON trace tree, making debugging and performance analysis far simpler. Guardrails frameworks, such as NeMo Guardrails or Guardrails AI, act as middleware layers in your LLM architecture. They sit right before the LLM input and after the output, intercepting data to validate safety, block PII leaks, check for prompt injection, and verify formatting. For example, a healthcare bot might use an output guardrail to block unapproved medical diagnoses, replacing them with a generic disclaimer. This ensures compliance and safety in sensitive applications. Securing personally identifiable information (PII) in LLM pipelines is non-negotiable. Implement an anonymization pipeline such as Microsoft Presidio before data leaves your system. Replace sensitive entities with pseudonyms or hashes and only de-anonymize responses internally using a secure state map. For example, a user's name and credit card are transformed into placeholders before hitting the cloud LLM API, ensuring that sensitive data never leaves your local environment. LLM routers or gateways, like Kong, LLM, or Portkey, standardize multiple upstream provider models behind a single API. They handle automatic retries, fallback options, load balancing, cost tracking, and global rate limiting. For instance, if OpenAI's API fails, the gateway can reroute requests to another provider like AWS Bedrock, ensuring uninterrupted service for users. This abstraction simplifies integration and boosts reliability. Automated regression testing for prompts is crucial in a CI/CD pipeline. Set up a GitHub action that triggers when a prompt file is modified. The workflow runs evaluation scripts against a representative dataset using an LLM as a judge. If the new prompt version scores below the baseline, the build fails, preventing deployment. For example, if a prompt update misses critical compliance steps, the pipeline blocks the change, maintaining quality and compliance. The LLM is an open-source LLM serving engine designed for high throughput. Its innovation page attention manages attention key value memory like virtual memory paging in operating systems. This eliminates fragmentation, allowing multiple requests to share memory efficiently. For example, an enterprise can scale from handling 10 to 150 concurrent user streams on the same GPU, thanks to VLLM's optimized memory management. Semantic drift occurs when the distribution of user queries changes over time, often due to new trends or features. Monitor this by extracting embeddings from incoming queries, calculating their vector space distribution, and alerting if there's a significant shift from the baseline. For example, when users start asking about a new product, the monitoring dashboard detects the shift and alerts engineers to update the underlying documentation. Protecting your API budgets requires intelligent rate limiting. Instead of counting raw requests, implement a token bucket or leaky bucket algorithm at the API gateway based on total estimated tokens consumed. This approach prevents a single large request from exhausting your quota. For example, if a user tries to summarize a 300-page book, the gateway blocks the request before it consumes the entire team's daily budget. Understanding the architectural difference between synchronous REST endpoints and WebSockets is key for LLM chatbots. REST is stateless and not ideal for long-lived streaming responses, while WebSockets provide persistent bidirectional communication. This is perfect for interactive agents that require constant state updates and interruption signaling. For example, a user can interrupt an AI voice agent mid-sentence via WebSocket, creating a natural conversation flow. Cold start problem in LLM microservices arises when serverless containers must pull and load large model files into GPU memory before serving requests. This can lead to significant delays for the first user. Mitigation strategies include using always-on provisioning, caching model weights on shared file systems, or optimizing base engines. For example, keeping a single warm container alive can reduce startup latency from 45 seconds to near-instant responses. Scaling vector databases like Pinecone, Milvus, or Qdrant horizontally involves data sharding and replica pooling. Sharding splits the vector index across multiple nodes, while replica pooling duplicates shards for concurrent read queries. For example, an e-commerce site can handle 100 million products by sharding its database across several nodes, ensuring fast, parallel lookups and low search latency. Robust fallback strategy is essential for LLM system resilience. This involves a tiered architecture, retrying with exponential backoff, failing over to an equivalent model on another provider, falling back to a lightweight open source model, and finally returning a polite error if all else fails. For example, if OpenAI's endpoint is rate limited, the backend silently reroutes prompts to an Azure deployment, ensuring users aren't disrupted. Tracing individual agent spans is crucial for debugging complex LLM workflows. Agents often call multiple tools and make several internal calls before returning an answer. Without discrete spans, you can't pinpoint where failures occur. For example, if a data analysis agent outputs an incorrect calculation, tracing reveals whether the issue was with the LLM's reasoning or an external tool's outdated data. Figuring the right metrics on a Grafana dashboard is key for monitoring LLM applications. Track system-level metrics like GPU memory utilization, API request rates, and error codes. At the AI level, monitor token counts, latency distributions, semantic cache hit rates, and cost per user. For example, set up Slack alerts for high rate limit errors, enabling your team to scale fallback instances proactively. Blue-green deployment maintains two identical production environments. The active environment runs the current model while the new model is deployed to the secondary environment. Automated tests are run, and once passed, traffic is switched instantly, minimizing downtime and allowing safe rollback. For example, switching from GPT-4 to a fine-tuned model is seamless and reversible with this approach. Safely expose internal databases to LLMs. Use an isolated read-only API layer. Never allow the LLM to generate raw SQL commands. Instead, provide parameterized APIs that validate and sanitize inputs before querying the data warehouse. For example, expose only specific endpoints like get user orders, ensuring all queries are safe and controlled. Retrieval augmented generation, RAG chunk versioning ensures that when knowledge-based documents change, vector representations are updated accordingly. Each document chunk is tagged with a timestamp or hash. When a document is modified, old chunks are purged and new ones are indexed, preventing retrieval of outdated information. This keeps your LLM responses accurate and up-to-date. Strict JSON schemas enforce deterministic compliance from open models, ensuring that downstream microservices can confidently map fields without risking type errors or crashes. For example, an automated billing agent outputs invoice details using a schema where price must be a positive float, preventing system failures from unexpected data types. Effective logging is the backbone of production readiness. Ensure that logs capture all relevant metadata, including prompt inputs, outputs, latency, and errors. Structured logging formats such as JSON make it easier to integrate with monitoring tools and trace issues across distributed systems. This practice enables rapid troubleshooting and continuous improvement. Monitoring is essential for maintaining healthy LLM pipelines. Integrate with tools like Datadog, Relic, or Phoenix to visualize system health, track anomalies, and set up alerts for critical events. Real-time dashboards provide visibility into latency, error rates, and throughput, allowing teams to respond quickly to incidents and optimize performance. Continuous integration and continuous deployment (CI/CD) pipelines are vital for LLM application agility. Automate testing, evaluation, and deployment steps to ensure that only validated changes reach production. This reduces manual errors, speeds up delivery, and maintains high quality across all updates. Dynamic prompt fetching allows backend applications to retrieve the latest prompt versions on demand. By tagging production-ready prompts and exposing them via APIs, teams can update prompts without redeploying code or restarting servers. This flexibility supports rapid iteration and consistent user experiences. Semantic versioning provides a clear, standardized way to track prompt and model changes. By incrementing major, minor, and patch versions, teams can communicate the impact of updates and ensure compatibility. Tagging production versions helps distinguish stable releases from experimental ones. The API gateway layer is the front door to your LLM application. It handles authentication, rate limiting, request routing, and monitoring. By centralizing these controls, you can enforce security policies, manage traffic, and gather metrics efficiently, all while simplifying the client interface. Load balancing distributes incoming requests across multiple model instances or providers, preventing overload and ensuring high availability. Techniques like round-robin, least connections, or weighted balancing can be applied at the gateway or service mesh layer, optimizing resource utilization and user experience. Tracking and optimizing costs is essential for sustainable LLM operations. Gateways can log token usage, request counts, and provider costs, enabling teams to analyze spending patterns and set budgets. Automated alerts can notify you when usage exceeds thresholds, supporting proactive cost management. Global rate limiting ensures fair usage across all users and prevents abuse. By implementing token-based limits at the gateway, you can control overall consumption and protect shared resources. This is especially important in internal developer platforms or multi-tenant environments. Monitoring latency is critical for user satisfaction. Track average and percentile response times as well as time to first token (TTFT). High latency can indicate bottlenecks in model loading, network, or downstream services, prompting targeted optimizations to improve responsiveness. Tracking error rates such as 4xx and 5xx codes helps identify systemic issues and trigger alerts. High error rates may signal upstream provider outages, misconfigurations, or application bugs. Proactive monitoring enables rapid incident response and minimizes user impact. Semantic caching stores previous LLM responses to similar queries, reducing latency and cost. Monitoring cache hit rates helps evaluate the effectiveness of your caching strategy and identify opportunities for further optimization. Tracking cost per user metrics provides insights into the efficiency and scalability of your LLM application. By analyzing token usage and associated costs per user, you can identify heavy users, optimize pricing models, and ensure fair resource allocation. Automated alerts tied to monitoring dashboards enable teams to respond quickly to incidents. For example, if rate limit errors spike, alerts can trigger scaling of fallback instances or rerouting of traffic, maintaining service continuity during peak loads. End-to-end evaluation testing ensures that new models or prompts meet quality standards before going live. Automated tests simulate real user interactions, checking for accuracy, compliance, and performance. This reduces the risk of deploying faulty updates. Safe rollback mechanisms allow you to revert to previous model or prompt versions if live metrics degrade. Blue-green deployments and version tagging make it easy to switch back instantly, minimizing downtime and user disruption. Always-on provisioning keeps at least one model container instance running at all times, eliminating cold start delays. This is especially important for latency-sensitive applications, ensuring users receive instant responses even after periods of inactivity. Caching model waits on shared network file systems such as PVCs, speeds up container startup times. This approach is particularly useful in serverless or containerized environments where large model files can otherwise cause significant delays. Using highly optimized base engines for model serving reduces resource consumption and improves throughput. Open-source solutions like vLLM leverage advanced memory management to handle more concurrent users without running out of GPU memory. Sharding splits vector databases across multiple nodes, while replica pooling duplicates shards for concurrent reads. This architecture supports massive scale, low latency, and high availability, making it ideal for large product catalogs or knowledge bases. A tiered fallback architecture ensures your application remains resilient under failure conditions. By layering retries, provider failover, open-source backups, and user-friendly error states, you can maintain service even during outages or rate limits. Execution traces provide a detailed view of agent workflows, capturing each tool call and internal step. This granularity is essential for identifying root causes of failures, whether they stem from model reasoning, external tools, or orchestration bugs. Strict schema enforcement ensures that all data exchanged between services adheres to expected formats and types. This reduces the risk of runtime errors and supports robust, maintainable production systems. Summary: production readiness for LLM applications requires a holistic approach, combining robust logging, monitoring, prompt versioning, secure data handling, and resilient deployment architectures. By following these best practices, you can deliver reliable, scalable, and secure AI solutions that stand up to real-world demands. Thanks for joining this comprehensive guide to LLM production mastery.